Welcome to another video tutorial. Today we are going to explain the determination of Planck's constant experiment by using virtual lab. So as you can see here, we have the experimental setup for the determination of Planck's constant, and this is in the platform of virtual lab. So we have the experimental setup. So before going through the experiment, we will look at the theory first. And for the theory, we have to determine the Planck's constant. So let's see what the Planck's constant is all about. Actually, it's early 90s when Max Planck gave his idea about the quantized nature of the light. So before that, basically people out here in the science community, it is proven that light has only the wave nature. So it's only the Max Planck who actually gave the idea about the quantized part of the light. Later on, the Einstein's photoelectric effect has proven it as that Planck's was correct. Light has dual nature. One is wave, another is the particle. So in terms of particles, light's termed as photon. So that if the photon has a frequency nu, the energy of the photon will be equals to h nu, where h is termed as the Planck's constant. So here in this experiment, we will try to find out the value of this h using a very simple experimental setup. To relate the theoretical idea with the practical setup, let's go through very basic part of this setup, that is called the LED. So an LED actually stands for the light emitting diode, so which is nothing but is a special kind of diode. We know that a diode is nothing but a PN junction formed by PN junction. So this PN junction is not exactly the sandwich between the P and N. It's different. Actually, in case of the thin film, for example, the p-type material is actually grown on the n-type material, or maybe or n-type material may be grown on the top of a p-type material, and it also depends on the dopants. So type of dopant you are using, so you can convert an intrinsic semiconductor into either p-type or n-type, or you can grow a n-type inside a p-type. So that's the way we actually form a p-n junction. So we can discuss on this thing later, but let me describe you what happens in the LED. So eventually, when there is no bias, that means when there is no voltage applied on the P side and N side, as we can see, this is actually the LED what we see in our daily life. So this is called anode, this is the P side, and this is the cathode, this is the N side. So we have to make it in forward bias. So that means we have to connect a positive part of the battery with this part, that means the anode part, and the negative part of the battery with this cathode part. And this is the diagram of the LED as we use during the circuit. So this is the P side and this is the N side. So in the forward bias, P side is connected with the positive side of the battery, and the negative side is connected with the negative side of the battery. So this is what actually happened, what is there inside the LED, you can see. Now what is happening? Now let's get to it into it. So when there is a p-n junction, as we know that there is a space charge region, or called immobile charge region, we called it depletion region. So there is a built-in potential inside this p-n junction. In this part, there is called the depletion region when there is no bias. When there is a forward bias, this depletion region actually reduced, and when it got the cut-in voltage, the depletion region vanishes and the current due to the diffusion takes place, and this diffusion current actually causes the recombination of the carrier. That means the electron recombine with the hole to generate energy, and this kind of energy is called the radiative radiation or the radiative energy. There is another type of energy is also associated with this one. It's called the non-radiative recombination, where actually those actually give rise to the temperature, and we all know that is in that case the phonon involved. Let's discuss all these things later on. So what is happening? Let's stuck with the radiative recombination. This hole and electron recombine and they give rise to the light, and as we see in case of the light emitting diode, something is coming out of that light. So this is all about how the LED actually glows. So when we give the forward bias to the LED, we find the light is coming out of this LED. Now very simple, as we have observed, some of us have observed before that one, that if we applied an arbitrary voltage, say 0.5 or 5 or 1 volt, not all the time we found that LED is glowing. It needs a certain voltage, that is called the cut-in voltage, for the LED to be glowed. So that's cut-in voltage, sometimes called as knee voltage. We have to find out the knee voltage. So what will we do with that knee voltage? So in that virtual lab, that is theory is given, as we can see in the theory part, that this light energy, it's called the E is equals to h nu, as we have seen before, that this E equals to h nu. This nu is nothing but the frequency and can be termed as c by lambda. So if you put the value here, this E equals to E becomes hc by lambda, and eventually this is the expression, this equation number 1. Now let's have a look on the forward bias condition. When we forward bias it, when it reaches the knee voltage, then only there is emission of light. What happens actually? The electrons and holes recombine. So this energy is given by nothing but the applied voltage, and to convert it into the energy term, we need to multiply with the electronic charge. So it's EV. Whenever we reach a voltage that is called the knee voltage, this V is called the knee voltage here, it actually gives rise to this energy, and hence this energy is converted into the emission of the photon, and we get this lambda. So if we put the value of E here, we have EV equals to hc by lambda, and hence this V is giving as hc by E into 1 by lambda. Now as we can see, we have to find out the value of H, we know the value of C, we know the value of E. How to get that one? For each color of LED, for each LED we have 4 colors. For each color we have 1 LED. So for a particular color, that means for a particular lambda, we will get a particular V. So suppose we have 4 colors. Let me show you. Here we have 1, 2, 3, 4 and 5. This is unknown. This blue has a wavelength of 475 nanometer. Please keep it noted in your copy. So this blue is actually 475 nanometer. So red is 650 nanometer, green and yellow, they have a different wavelength. So if I come back to this one, so for each lambda 1 we will have a different V1. This is a lambda 1 for V1. For lambda 2 value, that means for different value of the wavelength, we will have a V2. For lambda 3 it will be v3, for lambda 4 it will be v4. So we will have 4 points, 4x and 4y, and let us suppose that this lambda is nothing but the x in the x portion, this 1 by lambda, and this v in the y portion. And how to measure this 1 by lambda and v, we will discuss it later using Excel sheet. So let's come back to this hc by e value. This hc by e value is termed as s. Why is it so? So let's look at this graph. This v is in along the y-axis. Now this 1 by lambda is in the x-axis. Now when we will plot the graph, plot the point first and then followed by the joining the line. So what we will get a straight line like this. Now in this straight line curve, we have a cut from this graph. Actually, this is, if we join this point with this point and this point with this point, we will get a difference of v value, two v values. Suppose this is v2. Suppose not that v2 is not the what we have got from the data. Mind it, this is an arbitrary point from the graph. We are not considering the points, the 4 points. The 4 points are different. We have used the 4 points to draw the line. Now we have taken any point, any arbitrary point from that line that shouldn't be any of those 4 points. That should be a different points of that line. The line, actually one line has numerous numbers of points, so you can take any points. So from here to here, this is actually called the delta v, and this is called the delta 1 by lambda. When we divide this by this, we'll get a slope, and this slope is nothing but v slash 1 by lambda. This is called the s, and this s is nothing but equivalent to this hc by e. See, now when we will get the value of this delta v by delta 1 by lambda, that means the s value, by taking this e and c in this and the other part of the equation, we can easily get the value of h. So this is the way to measure the value of h using the graph only. We will not use a direct value of v and 1 by lambda to get the h value, but we will use that the graphical method. So let's go back to the experimental setup. So we have this experimental setup with us. So as we can see, in the experimental setup, we have this diagram where we can see this is the voltage, that is called, and it's not a voltage actually, this is the battery where we can apply the voltage. It's a rheostat. By the use of this rheostat, we can usually change the value of the applied voltage. This is the LED, this is the voltmeter, and ammeter is connected with the series with this resistance. Now let's connect these circuits. So we have connected the circuit according to this one. We have to insert the key here. The insert key option is here. So let's start with this red LED. I will perform the experiment for the red LED, and you have to go through this green LED, yellow LED and blue LED as homework. So let's go with this red LED. I will change this one, increase the value, and see at certain point the LED will glow. So what value we should take? We should not take all these values. So we have to take the value for which the LED just glows. So this is called the new voltage. So let's find out this value of the new voltage. Okay, so it's somewhere here. it's of okay 1.908. So this knee voltage for the red LED is 1.908. As you can see, if we reduce the voltage by a certain amount, as there is no current actually, you can see. So let's go back to the value, increase it. Okay, we got it as 1.908. So we have another option. So we have green, we have the yellow, so we have blue. This for blue it's 475. It's not given here, but I'm telling you this one. And we have another one. This is the infrared. So let's go back to the okay, let's find out for the infrared first. And for the infrared, as we know that infrared is not visible to our eyes, so we can't expect that our light will glow here. So what we have to look at, we have to look at the current value. When that will be, it will be in forward bias, so there will be a diffusion current, and this diffusion current, that current will be shown by this value. So let's look at this current value where it is increasing. Let it increase a bit. Okay, I'm just increasing it. So see, so this is 1.1028, so that means it has reached its knee voltage. Now let me decrease it. Okay, please be sure this is 1.188 something like this. I'm decreasing it again. Okay, so this is 1.116, no current. 1.121, this is a certain amount of current. So we will take this value as the knee voltage for the infrared. So we have actually made a table. Let me show you the table. So what we have, it's that only. So let me go to the table. So we have here the table for the light. So in this case we have the different colors of LED. Correspondingly we have different wavelengths in nanometer. So we have to convert it into meter. So how to convert it into meter? We have to multiply this value with 10 to the power minus 9 to get it in the meter. So likewise in this case also we have to multiply it with 10 to the power minus 9 to get it into meter. And I'm just leaving these things for homework basis. So how to get the 1 by lambda value? A simple value, 1 by this value, simple one. Now coming to the knee voltage, as we have seen that for the red LED it's 1.908, for which we got the just glow condition. And for the infrared, that means the unknown whose lambda is to be calculated. This all are to be calculated as a second task. So we have only the knee voltage for that one, and we have to find out the unknown voltage using this formula. Now I have performed this experiment, and before that I have got some data for the yellow, green and blue correspondingly, and then I have found that wavelength, I have found that 1 by lambda, and I have put it in a graph, and I have got a graph like this. Let me show you the graph. So we now at the graph part. So I have used the origin to plot the graph. This is origin 2021. So what you need to do, you need to plot it in the 1 mm graph paper using the pencil only. So here you can see these are the 4 points. 1, this is the 2, you can see the values. Okay, so let me not show you the value, so you have to do it. by your own. So this is the voltage axis, this is the 1 by lambda axis, this is the name of the graph, V versus 1 by lambda curve, and you have to mention the one smallest deviation along the x-axis and one smallest deviation along the y-axis. This will be in a particular value. So as we mentioned, this is in volt, you have to mention in volt here in the y-axis and in the meter inverse in the x-axis. Now about this scaling in the upper portion, that means you no need to be mention it, you have to mention only the left and the below one. So wherever you got this one, you just tick it, you just give a tick on that one also. Now what to do with this graph, let me show you with the help of another thing. So now we are with the graph only. Now I think, yes, it is. So we are now with the graph. So what we have to do, after drawing this graph, after connecting the 4 points, we'll get a straight line, and then we have to extend this straight line up to a certain value. So it will go through the, you can see this, it will go through the 0 0 origin. So let me keep it up to this. Now what we will do, we'll actually find out the slope of this of the curve. Now don't take this line originated from any of the point you have found. So let us take from this value. So this is it. Okay, okay, fine. So this is this one nothing but delta V. So how to calculate the delta V value? From the graph, the delta V value can be found very easily. I'm telling you how. So we have the one SD along x-axis and we have one SD along the y-axis. So this is the y-axis SD. This one is correspond to the y-axis smallest division, and this corresponds to the x-axis smallest division. How? I'm telling you. So we can easily count the number of smallest divisions along the y-axis. We can easily find it with the 1 mm graph. So there will be so many smallest division. Each 1 mm division is called as one smallest division. So suppose it has, for example, it has 20 smallest division, and suppose it has 18 smallest division along the x-axis. So along the x-axis, we know that one smallest division is some amount. It is some something. I don't know actually what is the value. So you will find it suppose A. So 1 is equals to A, and it is 18. So what we have to do, we have to multiply this 18 with the 1 SD value, that means A. So it will be 18A. So, and like in this case, in this Y value, we have suppose 20 SD. So you have to multiply that 20 with one smallest division value along the y-axis. So we will have this value and we will have this value also. So this is the delta V and this is the delta 1 by lambda. So when once we get the delta 1 by lambda value, delta V by delta 1 by lambda value, we will easily find out the value of the slope. So let's go back to the slope. So yes, we have this delta v from this part, and we have delta 1 by lambda from this part. So we will divide this delta v with the delta 1 by lambda to get the value of s. And now this s equals to hc by lambda, and from here we can easily find out the value of h. So this is the first part of the experiment. Let's go back to the second part of the experiment. In the second part of the experiment, what we do actually, we have this graph. Now, as we can see, what we can see, let me show you the Excel sheet. In the Excel sheet, you can see that for the infrared, we have the unknown wavelength. This is to be calculated. But what is known is the knee voltage. We have got this knee voltage as 1.121 volt. So what we have only this value, and please remember that corresponds to the y value. Let's go back to the figure, that means the graph. So in the graph we can see we have this 1.121. This is 1.5, this is 1.0, so this is somewhere, this is 1.25 if I'm correct. So this is 1.25, so 1.121 will be somewhere here. This is 1.1, this is 1.2, okay, this is 1.1. So suppose this is my 1.112, for example. I'm just taking it as a rough wise. So this is 1.1. What we have to take, we have to draw a straight line from this value until I reach a value up to here. That means this curve should be intersected by the straight line that is actually parallel to the x-axis, and it made the curve at this point. So let's give it a name, O. Now we have intersection at O. Now what we do actually, we will draw a straight line which should be parallel to this y-axis, and as a result it will intersect the x-axis. So let's draw. So it will be like this, roughly like this. So it will intersect the x-axis at that point. So from the intersection point we can easily find out the value of the x, that means 1 by lambda. It's very simple. Count the number of SD, multiply these smallest divisions with the 1 SD along the x-axis, you will get the 1 by lambda value. To have the lambda value, you just divide the value, you just divide 1 by this value, that means you have to take the reciprocal. When you have the 1 by lambda and you know how to get the lambda value, simply reciprocal. So that will be in the meter. Multiply this value with 10 to the power 9 to get it in nanometer, or you can get it in micrometer by multiplying it with 10 to the power 6. So it's up to you. So that's all for the measurement of the Planck's constant as well as the find out the unknown wavelength. So let's revise all the things we have. So we have this Planck's constant experiment setup. Here we have done the experiment. We have found the knee voltage for different LEDs. We have, for some LEDs we have the known wavelength, for some LEDs we don't have. So we have two tasks. One task is to find out the value of H, that is the Planck's constant, using this formula and using the graph, and the second task was to find out the unknown wavelength, that means the wavelength of the infrared LED. So we have done all these things. We have gone through the theories of Planck's constant, we have gone through the theory of the LED, how LEDs work now, and we have gone through the formulas, we have gone through the graphs, and we have successfully performed the experiment to get the new voltages. And that's all for today. And using this virtual lab, you find out all these things what we have mentioned here now. So you can subscribe this channel for to be updated with the latest videos. So thank you to all for today, for having this lecture, this tutorial. So on the next video we will come with a different kind of experiments using the virtual lab. Thank you.